Yeah, thank you all for having me. Yeah, so today, well, I guess I should give a disclaimer. So this is a robotics talk that doesn't have a single robot in it. A lot of what I'm going to talk about today is the theory of what we need to do to take a lot of the really wonderful work that's been done in recent years in probabilistic safe learning and actually make it work on robots. The goal of my research, and I'm sure many of yours, is to get robots out of the lab and into the real world doing this huge myriad of different tasks in different environments, right? And it's completely intractable to send robotics experts out everywhere to program robots to function in these environments, doing the things people want them to do. So we need tools like imitation learning, right? And these demonstrations that show the robot what to do could be kinesthetic. They can be the robot using cameras to watch people do it. It doesn't really matter what form they're in. But the point is that end users can pretty easily show robots what to do. And there's been tons of great work in this in the past decade or so. But one of the issues is that while there's been tons of good work in imitation learning, our way of doing things typically is to throw some data at the algorithm, develop a really nice algorithm, cross our fingers, and hope it works, right? But as roboticists, it's not super uncommon for us to see results like this, where we show the robot how to make cereal, and it does something that's a very rough approximation of the task, right? But it is not what we actually want to happen, right? In this video, it's a joke. It's made by Simone Gertz, who does the shitty robotics channel on YouTube. But to roboticists, this isn't really a joke, right? Like, it's super common to see things like this happen, and nobody is going to want to use robots if this is what happens when we train them, right? And so what I'm going to argue is that we need imitation learning, but we need safe and correct imitation learning. And that people have confidence in that it's going to work. And what I mean by safe and correct is that I want a robot that I can show something to, and it can either tell me, I get what you're trying to show me, I think I can do it almost as well as you, or I'm not sure, I think I need more data, right? What does it really mean computationally to get the gist of what someone is showing you? So before I go any further, I should just define safety. It's a super loaded word that means different things to a great number of people. This isn't even close to a full taxonomy. There's a pretty nice OpenAI paper from a few years ago that does give one. But some people talk about formal safety, with respect to a model, risk sensitive, like in finance, robustness with respect to adversarial examples, monotonic learning, safe exploration. There's tons of different ways to think about safety. For the purposes of this talk, I'm going to use a really sort of broad umbrella definition that I think encompasses most, if not all, these, which is just that when I say safety, what I really mean is correctness plus confidence. We have some measure of performance that we want to meet or exceed. So this could be total reward you get. This could be never going into certain blacklisted states. And we want to have confidence that we're actually going to meet this correctness metric. This could be a hard guarantee with respect to a model. This could be a probabilistic guarantee. And if we look sort of historically at how people have achieved safety, there's sort of this spectrum. If you look at one axis of it, we can think about the strength of guarantees that are provided. And on one end, we have these methods that require perfect models that often come from like the verification and synthesis communities, which we just don't really have in robotics. And so these are not always useful for all types of problems that we want to address in robotics. And on the other end, right, we have these methods that you might be familiar with, like TRPO or constrained policy optimization, where they're built on this like really nice theory of monotonic learning, but then you have to make approximations along the way. And with those approximations, we lose any kind of real guarantee, hard or probabilistic, that we're actually being safe, right? And so that's not very satisfying for robotics either. And so what I want to argue is that we want something sort of in the middle. We want to use probabilistic methods, things kind of like what have been developed in like the PAC-MDP community. People have used concentration inequalities. But the biggest problem for robotics is that these methods are horribly sample inefficient, often requiring like tens of millions of samples to do anything reasonable. And so a lot of this talk today is going to focus on probabilistic notions of safety and going in and addressing bad statistical assumptions that have historically been made in these methods so that we can do what we want to do a lot more efficiently and have safe imitation learning that can actually scale up to robotics. OK, so the talk's going to be in 3 parts. I'm first going to just introduce some theory about one instantiation of what safe imitation learning can mean and a pretty basic algorithm to achieve it. This algorithm is going to make 2 really bad assumptions. One, that we have either perfect models or time to collect tons of data inference time. The second bad assumption it's going to make is that we can do perfect policy evaluation. And in the next two parts of the talk, I'm going to sort of address those and show how to fix these issues by coming up with an inverse reinforcement learning algorithm that does not need models or this kind of data, and a way to do approximate but high confidence and efficient policy evaluation. OK, so we'll start with the theory of safe imitation learning. So here's how I'm going to define the safe imitation learning problem. I'm going to say that what we want to do is we want to upper bound the policy loss, essentially how bad the robot could do compared to the human demonstrator, or the expert, on the ground truth reward function. And we want to be able to bound this policy loss with high confidence, even though we don't know the ground truth reward function. So this is what's tricky about it. Safe reinforcement learning, in fact, is even really difficult, or even safe policy evaluation, where we know the reward function, and we just want to bound like how bad a policy can do with respect to an expectation. This is one step harder, in that we also want to bound how well we're going to do against a reward function that we don't actually know, right? And so this kind of requires some theory of mind, right? Where you have a robot, it gets some demonstrations, it has to imagine, like, what was the person thinking when they gave the demonstrations? What's the distribution over all the possible reward functions they could have had, et cetera. So this is sort of dealing with double uncertainties. And I'm going to cast all this in an inverse reinforcement learning framework. And so if you're not familiar, or if you just need a quick brush up, I just want to go over some basic facts about sort of the original IRL algorithm from BIRL in 2004. So the basic idea was that they considered a reward function to be just a weight vector. So your reward is a linear combination of potentially nonlinear features. So it's still a very general way to express this. And if we want to look at the expectation of the expected value of a policy at some start state drawn from some starting state distribution D, we can just write this as an expectation over the discounted rewards, right, that you're going to get from running policy pi. We know these rewards, based on how we just defined reward, is just a weight vector times these features. Pull out the weight vectors from the expectation. And what we get is a weight vector dotted with these expected discounted features. We're going to call these the discounted feature expectations, or mu of pi here. And the basic idea behind this original algorithm was just to find a reward function that if you compute the optimal policy with respect to that reward function, you're going to get feature expectations that match the expert's feature expectations. And the insight behind this was that if you match the expert's feature expectations, that because reward is linear in features, right, that the total return, expected return, is going to be the same. And we are certainly not the first people to think about trying to bound how well you're going to do with respect to the expert, even though you don't know what the reward function is. And in fact, in this paper and in the follow-up from Saeed and Shapir in 2008, they came up with an even tighter bound. And they did provide a bound for this, but the bound is incredibly loose. But here's the basic argument that it uses. It uses this sort of Hufting-style concentration inequality bound, where what they try to show is that based on the number of demonstrations you see in M, you can essentially bound how tightly you can know the feature these expected feature counts, right? And again, because return is linear in these expected feature counts, if you can bound how well you know the feature counts, and you assume that you can match any particular feature count exactly, then you can bound how poorly you're going to do with respect to the demonstrator. Now, one thing to notice here is that there's a lot of things that are either being assumed or not being taken into account, right? This is just like a counting-based sort of argument, right? You're just doing a really simple concentration bound. It's not thinking about the actions that you could take or alternatives that can be taken. In fact, it's not looking at actions at all, right? It's really just looking at these feature counts. And it's not considering how likely any particular reward function is, right? It's just using purely worst-case reasoning. It's saying, if my reward function, or sorry, if my feature count expectations that I'm estimating are off by a certain amount, is there some like worst-case reward function out there that could really punish me badly, even if that reward function is really not very likely to happen? So the first assumption that I want to address is this assumption that if we don't know the ground truth reward function, the best that we can do is just using worst-case reasoning. And what I'm going to argue is that it is much more efficient to actually consider the likelihood of reward functions when we're assessing risk. And this is going to be based off some work we've done in the last couple of years. OK, so we're going to need a couple different ingredients in order to do this. One of them is Bayesian inverse reinforcement learning. You are also likely familiar with this, but just a quick primer. In Bayesian IRL, we are computing a posterior over reward functions rather than just a point estimate. And the idea is that you're just going to take a prior, multiply by a likelihood, right? And that likelihood is going to be Boltzmann. It's just going to say that we are essentially assuming that if we take any particular reward function and assume it's true, and we compute Q star with respect to that, that an expert is taking actions that are exponentially, or they're taking actions exponentially more often that look better under Q star. And that allows us to determine a likelihood of the demonstrations. OK, so that's one ingredient we're going to need. The second ingredient we're going to need is a metric that's often used in finance called value at risk. And the idea of value at risk is that if you take a bunch of possible outcomes that could happen, and you essentially just sort them all in order of how bad they are, right? What you can do is you can just cut off at some point that we'll call alpha. And that's going to give you the alpha value at risk. And that basically says that no more than 1 minus alpha outcomes are any worse than some amount of loss, which is called the value at risk, right? And so you want to be able to say something like, if you know this distribution and you're just looking at like the inverse CDF of it, you just want to be able to say something like, well, based on this distribution I know, if I use some particular investment strategy, I want to know with 95% confidence that I'm not going to lose more than $100, right? And that's the kind of thing this is used for. But if you don't actually know the closed form of the CDF and you want to compute this with samples, you need to do something else. And so we just suggest that you should add a single-sided confidence bound to this. And so the idea is then with a single-sided confidence bound on the value at risk, you can make statements like, with probability 1 minus delta, no more than 1 minus alpha % of the outcomes will be worse than X. And then what you can do is you can fix some risk level that you find acceptable, like, well, I'm OK with losing up to $100. Any more than that, I want to know I'm not going to lose more than that with high confidence. And you can just see if when you solve for X, if it's more or less than $100. And that lets you make a decision, right? So this is the second ingredient we're going to need. So here's how we put them together to come up with a simple instantiation of a safe imitation learning algorithm. So we get some expert demonstrations. We stick them into Bayesian IRL, right? And we do MC-MC. And that's going to give us a posterior over reward functions, or samples from the posterior. So we're going to do a couple things. One, we're going to take the map, the maximum a posteriori reward function, and we're going to compute with an MDP solver. So again, this is that bad assumption that we have a model. We're going to fix this later. But we're going to compute the optimal policy with respect to that reward function that we'll call pi star map. Okay? For every other reward function that could have been true, Ri, we're also going to compute the optimal policy for each of those reward functions, pi star Ri. Okay? So then what we want to do is we want to compute the policy losses that could have occurred if we were wrong about RMAP. What if RMAP is not really the true reward function, but it was some other reward function Ri? How badly are we going to do because we made that mistake? So if we assume that the policy we're going to run at the end of the day is pi star map, the optimal policy corresponding to what we thought was the best reward function, if we run pi star map and see how well we do under some other reward function Ri, right? We want to see how much value we lose compared to if we actually ran the optimal policy under Ri, right? So if some other reward function Ri was true, how bad are we going to do in comparison to the optimal policy under that reward function, right? So this is going to give us a whole bunch of different policy losses that could be true, right? And what we're going to do is sort them, compute the value at risk, add a single-sided confidence bound. And now we can ask exactly the question that we wanted to ask before. We can, if we pick some delta, we pick some alpha, we can say, OK, how much worse am I going to do than the demonstrator with a confidence of 1 minus delta, 1 minus alpha of the time, how often will I do worse than X, right, compared to the demonstrator? And I can pick those constants. I can pick an alpha, I can pick a delta, and I can pick an X and say, well, I want to make sure I don't do any worse than this compared to the demonstrator. And if the robot can say that that's true, then great. We don't need any more data. If the robot cannot say that's true, then it can request more data. And it could request this in multiple ways. It could just say, hey, I need more demonstrations. That puts a lot of onus on the demonstrator. But it can do something smarter too. And so we have a couple different active learning-based ways of doing this. One of them sort of information theoretic, and that is trying to just reduce uncertainty about the rewards and the reward functions in general. Another thing we've played with is sort of a risk-based criteria that tries to directly push down this value at risk estimate. And then you just do this again. And you want to ideally do it until the robot can say, hey, I get what you're trying to show me, and I think I can do it almost as well as you. So this is a nice idea, but it has these problems, right? It has this MDP solver in here that we need. So that means we either need a model or we need to be able to collect a lot of data. And it assumes that we can actually do this policy evaluation, right? And that we can do it perfectly. And neither of those things are true. So we're going to go in and address these issues. But first, how well does this work? So if we look at the efficiency of it, and we compare our way of computing this bound with the way that that Said and Shapir paper was doing it back in 2008, and we don't know of anyone else who's really looked at this problem since, we can see that the tightness of our bound when we just see a single demonstration is the same as the tightness of their bound when they see 23,146 demonstrations. So this is more than 4 orders of magnitude more data efficient. And again, it's because they're only thinking about bounding these feature counts. They're not thinking about actions. They're not thinking about alternative sort of counterfactual actions that could be taken. They're using worst case reasoning, right? Whereas we're actually thinking about the likelihood of any given reward function given the demonstrations. If all the demonstrations go left, it's pretty unreasonable to say, oh, well, the worst case might be to always go right, right? That's just not reasonable. And so we don't need to think about those. Or I should say we do need to think about those, but they need to be weighted with respect to their probability. And so this is way more efficient, and this starts to get us to a place where we can actually use this kind of algorithm on a robot, except for those terrible assumptions it's making. And we can do this without affecting the accuracy more than some epsilon that matches the confidence of our bound. And if we use this to actually judge risk of various policies based on demonstrations we see, we get some interesting effects too. So it's a pretty simple domain, but it's illustrative. So in this demonstration, this car driving domain, we show a demonstration that's avoiding cars, but it has no lane preference, okay? And then we say, okay, using either the Said and Shapir method or our method, we want to show the agent 3 other policies and have it rank how safe it thinks they are, really just how good it thinks they are. But we want to think about it in terms of risk. So which of these is like the least risky strategy? So one avoids cars but prefers the right lane. So it doesn't look a lot like this, but it's safe. This stays on the road but ignores other cars and sometimes collides with them. And this actually seeks out collisions. And it turns out if you use that original Said and Shapir bounding strategy, it gets the ranking of these completely wrong. It actually thinks this is the worst, even though it's the best. And again, it's because it's using this like feature count sort of based reasoning, right? It's like, well, this is kind of always in the right lane, and this wasn't. Whereas our method is actually thinking about this whole distribution and considering things based on how probable they are. And it turns out that based on the way that the demonstrator is acting, if you actually look at the actions, which theirs isn't, it's very unlikely that lane actually matters very much, but it is relatively likely that that not colliding matters. And if it does matter, it would make these really, really bad. And that's what our method finds, is that it actually gets this ranking correct. Yeah? Oh, just uniform right now. Yeah. So this is a really nice effect, that being risk sensitive gets you sensible behavior in these kinds of settings. OK, but none of this scales to robots, right? Because we don't have perfect models or MDP solvers that we can just use. We don't have perfect policy evaluation. So how do we actually handle this? So for this next piece, what I want to talk about is an inverse reinforcement learning model that we literally just got working about 4 days ago, although we had an earlier version submitted to ICML. And it's a way of doing inverse reinforcement learning without models or inference time data. So standard IRL actually has a couple really hairy problems. One of them is this one I've already mentioned, which is that it usually has policy learning in the inner loop somewhere. Methods like Bayesian inverse reinforcement learning, for every reward function they're considering, they often have to solve an MDP. Or other methods like GALE, generative adversarial imitation learning, have this kind of back and forth thing they do, where they do like a reward update, they do a policy update. But all of these require collecting data at inference time, right? It's not just based on the demonstrations. That's not great for robotics, right? The other problem is, and this is kind of weird, is that typically, these methods can't outperform the demonstrator in any significant way, except sometimes by accident. And the reason is that even though we like to sort of personify IRL and say, like, well, what it's really doing is, understanding the intent of the demonstrator. That's not really what it's doing. It's really doing something much dumber in some form of imitation. It's either just trying to match these feature expectations, or it's making some assumption that the demonstrator is optimal, right? And if you're assuming that, you can't really do better than the demonstrator. And so we have a new method that can address both these problems. And the way that we address this is by addressing the assumption that IRL should assume that the expert is near optimal. And we're going to show that there's significant computational and performance benefits to using actually suboptimal demonstrations that are ranked. So here's the idea. We have this algorithm that we call TREX, which stands for trajectory ranked reward extrapolation. And the basic idea is that if you have some demonstrations that are ranked, intuitively you should be able to look at them and roughly think, well, what seems to be sort of happening more in the demonstrations that are better or less in the demonstrations that are worse or whatever, and pick up on this trend of where things are going. And even if the demonstrations you've seen are all like really suboptimal, hopefully you can come up with some reward function that respects that ranking and can extrapolate to judge how good some trajectory is, even if it's much better than anything you've seen before. So it can extrapolate beyond the best performance you've ever seen. And so, if we graphed like the true performance of some trajectory under the ground truth reward function versus how like our reward model predicted, and we just trained on these blue ones, we hope that it will sort of extrapolate and either sort of be like linear or at least like monotonically increasing, so that things we think are better are actually better, right? And so the way we do this is by converting this RL problem that usually involves like MDP solving and planning and all these nasty things into a purely supervised problem where we come up with just a cross-entropy style loss function that basically just says that we should come up with rankings that respect the pairwise rankings. So what we do is we use a neural network to learn a reward function that is state-based, or in the case of like we do it on Atari games, we take a stack of 4 frames, put them through the network, it spits out a reward. And the intuition is that if we do this for every state or every set of frames in a trajectory, the trajectories that are better than worse trajectories should get more reward by our reward model, right? And probabilistically, we just say that the probability that some trajectory j is better than some trajectory I, it's just exponentially more likely that j is better than I if it gets more reward than I, okay? And so we just want to find some reward function that respects those pairwise constraints. And the really nice thing about this is it's fully supervised, right? There's no policy learning in there. We actually don't even need action labels, so this is actually a learning from observation algorithm. You have the potential for extrapolation if you regularize enough and actually get generalization. And it turns out that it works on quite high-dimensional problems like Atari with roughly about 10 demonstrations. And Atari has been a notoriously hard domain for inverse reinforcement learning to crack. There's really not much that has worked there yet. So how do we get this to work? And I think the biggest trick, right, is that if we just have 10 demonstrations, that does not give us a whole lot of data, right? That gives us like a quadratic number of sort of pairwise comparisons with respect to 10. That's not a lot. So we use a whole ensemble of data augmentation techniques to try to get more of these pairwise comparisons and to try to regularize a bit. So if we have a bunch of trajectories, this is a bit misleading. Not all our trajectories are of the same length. But we have a bunch of ranked trajectories from best to worst. One thing we can do is we can just subsample, right? We can say, well, if I take this chunk over here in this lower ranked trajectory, I'm just going to assume that it's better than this chunk of this trajectory over here. This has a couple nice effects. And it's not always going to be true. Maybe you'll get a really good chunk from a bad trajectory and a really bad chunk from a good trajectory. But on balance, this is generally going to be true. And it has some nice properties, too. So for a game like an Atari game where just living a long time might be good, since some of these trajectories are different lengths, right? Some live longer than others, and typically you live longest in the best ones. If you only look at full trajectories, it might just decide to be lazy and just give a constant reward all the time so that longer trajectories get more reward, right? But if you also force it to be able to correctly rank fixed length snippets from 2 different trajectories, right? it has to actually have a way of identifying what good play looks like, right? It can't just rely on time anymore. So this sort of pushes it into those kinds of solutions. We also do super sampling, and this helps fix that problem of, well, maybe I looked at like sort of a crappy part of the good trajectory and a good part of the bad trajectory or something. And we also do different variants of frame skipping, partly just to make this more computationally tractable and to get more variety. And we have a couple other techniques in our ensemble too that I'm not going to get into now, but that all have some nice properties and that seem to really strongly have a very strong regularization effect. So when you put this all together, here's what it looks like. So this is a plot like I showed before, where we have ground truth return on a trajectory versus prediction. And in red, what you're going to see are the trajectories we trained on. In blue are typically better trajectories than what we ever saw in training. And we want to see if we extrapolate correctly. And if we're extrapolating correctly, what we should see is either roughly sort of a linear relationship, or, again, at least a monotonic relationship, so that when something is actually better, we say it's better, right? And so we tried this on a bunch of different like Majoko tasks and Atari tasks. I'm just showing sort of a subset of them here. And here we have some nice success cases where we find these nice, almost linear relationships, right, that go well beyond where we saw demonstration data, especially in Hopper. But in things like Enduro and Ant, we found that here it's not even really fitting the training data very well. Here it fits the training data, but things kind of go crazy once we extrapolate. So this does not always work. I want to emphasize there are failure cases to this. But on the whole, it really worked very nicely in the vast majority of problems that we tested it in. And yeah? Do you have ideas for what characterizes the environments where this does? Yeah, we've been trying to figure that out. I mean, Ant happens to be higher dimensional than like Half Cheetah or Hopper, but then again, like it's working on Atari. So no, I don't. We're still digging into that. I wish I had a better answer for that right now. So here's some qualitative results first. So here are some demonstrations that we give for Half Cheetah that are ranked. So the worst only makes like 12 units of progress and just kind of crawls slowly on its face. This is like a faster face crawl, and this is a kind of unstable run, but that is actually reasonably fast. And what we find is that if we compare what T-Rex learns compared to the best demo, and when I say what T-Rex learns, I mean we do inference, like I said, and then we run PPO for some number of time steps. We can get significantly better performance than the best demonstration. So it's actually learning this coherent gate that goes beyond and is not just trying to match performance of the demonstrator. So we were pretty excited by this, but I mean, one question is, how's this stack up to just any old, even if you just learned like something really simple by accident, like make progress, maybe Gale and other methods would do almost as well. So I'll get to that in a minute. But we see the same kind of thing in Atari too, right? Here, the best demonstration gets a score of 600. T-Rex gets about 1,500, and learns this kind of qualitatively different strategy of sort of eliminating things column-wise and staying behind cover in a particular way. So qualitatively, looks great. So quantitatively, here's what we see. In blue here, we have the best demonstration. And then we compare in red and yellow to BCO, which is a state-of-the-art behavioral cloning from observation algorithm, and generative adversarial imitation learning. And then in green, we have the T-Rex performance. And if we gave T-Rex like 10 ranked demonstrations, what we did for Gale and BCO was we gave them 10 demonstrations of the same quality level as the best demonstration the T-Rex got to see, to make things as fair as possible in terms of data quantity. And so in fact, they kind of had a leg up because they got to see more good demonstrations. And so we see on a lot of these, and we do this for different stages as well. And by that I mean that for like Half Cheetah, we give demonstrations where the best one is pretty bad, the best one is medium, and the best one is actually pretty good. And what we compare that to is how well does PPO perform when we run it on the ground truth reward, okay? And so what we see is that consistently, T-Rex is doing significantly better than the best demonstration it saw, and it's also consistently surpassing BCO and Gale, which typically actually don't even do as well as the best demonstration. We see something similar in Hopper. Here, Gale actually sort of accidentally grabs onto something by being lazy. If it was being perfect and actually matching the expert performance, it would actually do worse, but because it did a bad job, it actually did a good job. So it does beat us in one occasion, but here, in stage 3, actually in stage 1, you see we get very close to actually even the ground truth performance if we actually knew the reward function exactly. And we do see failure cases, like in Ant, where we didn't have that good extrapolation behavior. We do pretty badly, although we still do better than Gale. And we see something really similar in Atari, too. As I mentioned, it's really hard to get other IRL algorithms like Gale working on Atari, and we're able to significantly outperform the best demonstration that we saw. And again, there are failure cases where we still do better than the competing methods, but not as well as the best demonstration. And if we look at sort of more qualitative evidence here, one thing we could ask is it actually grabbing onto reasonable features or not? So here in Space Invaders, what we see is if we look at across all the frames it ever saw, both during training and during learning, we can ask, what did you think was like the best frame and the worst frame you ever saw, or frame stack? And it rates this as worst, where all the aliens are there. It rates this as best, where there's a cleared screen with no aliens. And in fact, it never saw during training a cleared screen. And so this is evidence that it actually is doing extrapolation and grabbing on to meaningful features. And we also looked at sort of sensitivity, pixel-wise sensitivity of the reward function. And we see that in this min frame, where they thought was the lowest reward, it's not paying attention actually at all to where the agent is, or it's very, very faint. It's just paying attention to these shelters, the cover that it hides behind, and the alien positions, and most notably sort of the lowest, some of the lowest alien positions that are available. And so it really does seem to actually be paying attention to relevant things that make the ranking make sense and that allow it to extrapolate beyond the performance of the demonstrator. So another reasonable question is asking, how hard is it to actually get rankings, right? It might be kind of a high bar to just ask people, hey, you should just give me do crappy on some demonstrations and show me this variety of demonstrations. Yeah. Oh, here there's no prior. This is just purely a supervised learning task with a cross entropy loss. Yeah, and we did not pre-train the network either for visual features or anything like that. So yeah, it's kind of a high bar maybe to ask for rankings. Sometimes it makes sense to do that. Sometimes it doesn't. But I think there are a lot of naturalistic ways to get this kind of data. So one is in a game or a progress-related task like running or something, right? If you have access to a performance metric, you can use that as ground truth. But then you can use our method to infer a more dense reward function. Or even in a reinforcement learning setting, where you don't have demonstrations, you can just imagine the agent sort of practices on this reward function for a while that is very sparse. And then after a while, after it's improved, you kind of checkpoint that to get ranked demonstrations that are noisily ranked. And you just use our method to densify the reward, which you can hopefully learn faster from. And we've been doing some experiments with this recently. Or you could even, if someone's not very practiced at a task, you could even just watch them improve on the task over time, right? Or if you only have access to optimal demonstrations, you could do behavioral cloning on those. And then you could just add progressively more noise to the policy to get worse and worse demonstrations. And as long as you're in a reasonable domain where random performance does worse than the expert, this will actually give you something that looks kind of like the ranking you need. And we showed that even though these will give noisy rankings, that our method actually degrades. It definitely degrades, but it degrades fairly gracefully with noise in the pairwise rankings. So this is the percentage of pairwise rankings that are correct versus performance. And I think this was on half cheetah. OK, so what do we want to do with this? Well, we want to take T-Rex, and we want to create a Bayesian version of it. We want to plug it in place of Bayesian IRL in our safety method. And then we want to get it actually working on a visual, safe imitation learning, working on a visual robot manipulation task, like serial making. I think serial making is actually a really nice task in a lot of ways. To make IRL more efficient, there are several other assumptions we've been looking at addressing. One of them is this idea that demonstration data is almost always treated as being IID. That's definitely not true. And we showed that we can actually get significantly more efficient behavior in IRL if we assume that the expert is behaving approximately information optimally. And we actually have a nice sort of submodular optimization in here if you're interested in computing sets of optimal demonstrations for other applications as well. but I don't have time to talk about that today. So last part, we have this theory. We showed how to get rid of models in inference time data collection. Now we have to get rid of that assumption that we can do perfect policy evaluation. So some quick background. We're going to be in a finite horizon MDP. We're going to be working with stochastic policies, which is another terrible thing that I want to get rid of eventually, because who wants a stochastic walking controller? And I'm going to call trajectories H in the notation. So the problem we want to solve is safe off-policy evaluation. We want to have a probabilistic lower bound on the expected performance of a policy that is based on data generated from some different policy. So robot soccer, we have some walking policy we're pretty happy with. We want to try out some other policy without actually running it and having it fall over using the data collected from the old policy. Right? And so just some definitions here, right? Value of a policy, just like before. Expected returns based on trajectories drawn from pi, right? And we're going to call the policy that we want to evaluate, the evaluation policy, pi e. And these returns I'll sometimes just use shorthand G of H for. OK, so one way to do this in a non-safe way, or a non-high confidence way, is just Monte Carlo it, right? Collect a bunch of trajectories from pi e, average their returns together, boom. Zero bias estimate, right? But that's inherently on policy, right? So if we have off-policy data, we have to importance sample, right? So importance sampling, all you're doing is just taking those returns and you're reweighting them. You're just saying, how long or how often would have the evaluation policy done that thing versus how often this other policy that we'll call the behavior policy did that same thing, right? And so that's just how we're going to define the IS, or the importance sampling estimator. So this is an off-policy way of doing evaluation, but it still isn't high confidence. So how do you do high confidence? Well, I don't have time to get into that today, but there are a lot of methods out there that do this. And what they do is they determine a lower bound such that the value of the evaluation policy is greater than that lower bound with probability 1 minus delta. And there are a whole bunch of ways of doing this. A lot of them use concentration inequalities, kind of like that Hufting-style bound I showed before. But they're not very appropriate for robotics typically. And the reason is, I can just show you this graph without going into any detail about it. So this is from one of Phil Thomas's papers a couple years ago. He's one of my collaborators. He's actually on some of the work I'm going to talk about. Good friend of mine. I'm not attacking him. But I'm just pointing out that the x-axis here is 20 million, right? And that is not a reasonable number of trajectories to need to do anything, or state action pairs or whatever, right? These methods are not going to work for robotics. And one of the bottlenecks in getting them to work is efficient policy evaluation. If you can do efficient policy evaluation, you can do efficient high confidence policy evaluation. And one of the big bottlenecks is importance sampling. There are tons of statistical things wrong with importance sampling. And so I'm going to talk about one of those very briefly now. So the assumption that I want to address is one that is not universally believed, but I think in chatting with most people, you can get them to at least agree to this, that if you want to know something about some policy A, right, or your evaluation policy, and you say, you have no data to start with, you can gather data in any way you want. You can either Monte Carlo it and just run the evaluation policy, or you can run some other policy importance sample. I think it's reasonable to assume that the most statistically efficient thing you could do is just run the policy you care about, right? And it turns out that assumption is terrible. It's not even close to true. It can actually be much, much more efficient to use off-policy data. How much more efficient? Well, I'm not going to prove it, but I'm going to claim, and you can read the paper if you're interested, that there's what I would call an optimal behavior policy, pi b star. What do I mean by optimal? I mean that if you grab even a single trajectory from it and importance sample it, every single time you are going to get a zero bias, zero variance estimate of pi e. In other words, you'll get the value of pi e. In other words, you will get exactly the value of pi e every time, no matter which trajectory you sampled, right? Which just seems crazy. But just assume that this policy exists for a minute. How do you solve for the weights that should give each trajectory? Well, you just say that the importance sampled estimator using pi b star always equals v of pi e. Do a little bit of algebra, right? And we get weights that are based on, for a trajectory, that are based on the goodness of the trajectory, the value of pi e, so you need an oracle to tell you the thing that you're already trying to solve for, and the weights that pi e gives to h. And there's a pretty simple argument that shows that this policy does definitely exist if all returns are positive and transitions are deterministic. Even when that's not true, the same intuition holds that there are policies that are still a lot better for this kind of sampling. Yeah?
I think Monte just mentioned it, but it seems like everything's deterministic here, right? So
Yeah. So in this right here, this is all assuming deterministic. The same intuition holds, essentially, that even when this policy does not exist, for like when things aren't deterministic, for example, there's still much, much better sampling policies that are much lower variance. Oh yeah, yeah. So it's, but we don't have to prove that this thing exists because in fact the optimal one, when it's not deterministic, the optimal one does not exist. But there are ones that work much better because I can talk to you afterwards. The main reason though, it has to do with rare events and that you want to sort of oversample rare events, rare high magnitude events. Yeah.
Do you have an optimal behavior policy for any policy that you want to evaluate, or does it depend on the policy you evaluate?
It depends on the policy you want to evaluate. So if you notice, the weights for the trajectories, they depend on the weights for the evaluation policy. Yeah, so it's specific. And so the question is, if we don't already know this, that we can compute the weights, what can we do? Well, what we always do, gradient-based methods, right? So maybe you don't know the optimal behavior policy, but you can walk toward it. In other words, what you'd really like to do is you'd like to change the parameters of your behavior policy such that over time you're reducing the mean squared error of your importance sampling estimator directly. And the insight we had here is that you can't compute the MSE directly, because if you could, you'd already know the answer, right? But you can compute the gradient of the MSE, of your importance sampling estimator. And so when we do that, we go through a derivation that looks a lot like the derivation of the policy gradient theorem, and we get something we call the behavior policy gradient theorem. If you're familiar with the algorithm reinforce, this is exactly reinforce, what we end up coming up with, except instead of having the non-squared returns, we have the squared importance sampled returns here. And it turns out that if you follow this gradient for your behavior policy, you are going toward a policy that's going to lower the variance, or the MSE actually, of your importance sampling estimator. Importance sampling is unbiased though, so minimizing the MSE is the same as minimizing the variance. And what we show is across a bunch of different problems, we get this variance reduction. Just pay attention to the top two curves here, where if we just run, I think this is on cart pole or mountain car, if we just run normal Monte Carlo, we get some amount of variance, and with BPG, we get a very quick drop in the variance of the estimator, and it all happens pretty quickly within like 10 or so iterations. And this leads to modest sample efficiency gains, where we see the mean squared error of the estimator dropping faster when we use BPG. It's not a huge gain, but it's something we argue everyone should be doing if you're doing policy evaluation, because it's basically free. So there's very few reasons not to do this. But on its own, this is not enough just to like magically get policy evaluation working on robots. So we've been asking a lot of other questions too that I can't get into the details of today, but yeah.
Many algorithms don't do policy evaluation.
Right, they do policy improvement, right? Yeah, so it turns out that all policy improvement is essentially have a proposal for a policy, right? Check if with high confidence you think it's better than where you were before, and then if it is, take a step, accept that as your new policy, right? So that's one way of doing like safe policy improvement with only policy evaluation, and then you just need a good proposal mechanism. So there's been some work doing that. I think there are other ways of sort of integrating these ideas into policy improvement that we're looking into now. But that's a good point. Yeah?
It would be really cool if you could have some, for example, methods like converting and so on, they can also work on policy data or policy improvement. So it would be really cool if you could do something similar, but for policy improvement, that there's a behavioral policy that is better for policy improvement than the current policy.
Yeah, so on that front, we think there's really strong connections actually between the behavior policy gradient theorem and an optimal strategy for prioritized experience replay in something like DQN. So it's kind of like that, except your behavior policy is now a policy that's feeding you old trajectories, essentially. So we're working on that too. So a couple other assumptions real quick that we've looked at. One is that so far with importance sampling, right, we know what the behavior policy is, and so we just use it to importance sample. Now, one other thing you could do, it seems silly, but one thing you could do is instead, even if you know the behavior policy, you could just take the trajectories that you gathered from it, and you could regress an estimate of the behavior policy, and you could importance sample with that instead. It seems dumb, but it turns out that it's actually statistically better to use the empirical estimate of the behavior policy than the real thing. I was just talking to Rich Sutton about this a while ago, and he joked that all along we should have been using the empirical estimates, and that the how do you put it? The true behavior policy has just been a really bad estimate of the estimated behavior policy. And there are interesting statistical reasons why it's better to do this. And I can't get into it now, but we have a paper on it if you want to check it out. Another thing we've been looking at to get really large gains in robotic domains is using models. And I think there's been this historical assumption that biased models lead to biased estimators, which is true in most cases, right? But we show that there's a nice way of using models as something called a control variate to reduce the variance of your estimator without adding bias to it, even if the model is biased. And we combine some of these ideas with ideas from statistical bootstrapping to get a significantly more efficient way of doing policy evaluation. OK, so back to the high level. We want to put this all together. So I showed this theory of safe imitation learning. It made these bad assumptions of needing models or lots of data collection and doing perfect policy evaluation. We now have this way of doing IRL that does not require models or inference time data collection. We still need to make it Bayesian so that we can fit it into this framework, but we're getting close there. And I think this is just something of independent interest for the IRL community, especially because it scales to high-dimensional things like Atari. And we needed perfect policy evaluation up here, too. And we showed some strategies that we have and are continuing to work on that can do approximate policy evaluation with high confidence and efficiently, with robot-sized data. So I wish I just had some really cool robot video to show you that says, look, we've put this all together and it works. And we haven't yet. And we're in the process of doing it right now. But I think there's still some really challenging scaling questions. Some of them are just around seemingly silly things like stochastic policies. All this importance sampling stuff requires stochastic policies. It'd be great if there were insights from things like DDPG that just told us how to do this with deterministic policies, but it's really not quite clear yet. Also, I've been sort of pretending all along that we're working with real probabilities here, right? But there are these assumptions we made along the way, like someone is like a Boltzmann actor, for example, with respect to Q-star. I mean, I guess we're getting rid of BIRL, but the point is that there are all these baked-in assumptions in there that are not necessarily true, that I think that warrant human studies. And finally, I think there's only so much you can hope to squeeze out of state action pairs, right? There is only so much information there. And so I think one of the reasons why things like imitation learning have been so ill-posed and hard to solve is because we're ignoring a lot of really useful information. And so a lot of our current and ongoing work is looking at things like how can you use videos of related but maybe not the same task as sort of background information that the robot can use to infer things about intent? How can you use natural language narration of demonstrations or of interactive corrections to figure out which parts to really zero in on, how to generalize what's been seen, and how can you use things like human gaze to resolve ambiguities in what somebody is showing you? And so I think it's going to be really important going forward to sort of latch on to some of these extra modalities and not just pretend that the only information we have in these sorts of tasks are just state action pairs. So with that, none of this work obviously would have been possible without my really wonderful students in my lab, and I'm happy to take any questions.